So for this video, let's actually sketch the graph of the sine function. Now, what I could do is I could also show you how the sine function explicitly relates to the unit circle. So let's make another unit circle here. And we're going to look at how each particular special angle gives us a particular point on the unit circle with a particular height. So here's our unit circle. It's about right and centered. Good. All right. So remember, what sine of theta gives us is the height of point P on the unit circle for some specific angle in standard position. So we know that when we have zero radians or 0 degrees of rotation, we have an output value of 0 for sine of theta. What that corresponds to is the fact that if we don't have any rotation at all, the particular, it doesn't really matter what the x value is, but the particular y value is going to be 0. So a rotation, and that's what sine of theta gives us, right? This is sine of 0. Sorry, sine of 0. So when we have 0 rotation, sine of theta gives us 0 as the output. So let's plug that in. This, by the way, we're plugging these. What these corresponding pairs of values represent is some sort of ordered pair, right? So when we have 0 rotation, we have a point on the unit circle with 0 height. So 0, 0 is the point that we're going to draw there. Now let's look at pi over 6 here. So for pi over 6 radians, for that angle in standard position, if we plug that into the sine function, we'll get 0.5 out. So we can notice that, well, how many tick marks does it take to get to pi? Looks like it takes 6 tick marks. 1, 2, 3, 4, 5, 6. So that means every single tick mark along this x-axis here represents a jump of pi over 6 radians. So for this pi over 6 radians here, what's the output value? The output value is 0.5. So the output value for an input of pi over 6, excuse me, is an output of 0.5. And so we get this point on our graph. What would that correspond to on the unit circle? Well, we know that for an angle of 30 degrees, or pi over 6 radians, we would get another point with some x-coordinate. Doesn't really matter for now. We could call this x1, this x2. And we could get then some y value, and that y value is just going to represent the height of this point on the unit circle above the x-axis. And we know that that's 0.5 or 1/2, right? Because ultimately sine of pi over 6 gives us the y coordinate, or the height, of this point on the unit circle above the x-axis. So here we go. Now we know that for sine of pi over 3, we get an output value of, this might look funny, 0.86 repeating, but this might look more familiar to you as root 3 over 2. And by the way, it's not 0.86 repeating, actually. The number is not repeating. It doesn't have a pattern like that. It's irrational, so that's just a small point. Maybe just a little bit of an error there. So 0.86 is the decimal approximation for root 3 over 2. So when we have a jump, or when we have an angle of pi over 3 radians, the sine function will give us an output of 0.86, which is roughly going to be about right here. So again, here this is our value for pi over 6 radians. If we go another pi over 6 radians, then we're going to be at 2 pi over 6, or pi over 3. So this is pi over 3. And when we have an input of pi over 3 here, pi over 3, we get an output of root 3 over 2, or 0.86 roughly. And then let's look at pi over 2 here. So for pi over 2, this particular spot, when we have pi over 2 as our input, our output is 1. So for an ordered pair solution here, we have pi over 2 and 1. So pi over 2 and 1 is our solution here. So we can color that in. By the way, let's... I forgot to do the pi over 3. That's annoying. I forgot to do the pi over 3 angle. So here we have pi over 3 radians. There is some corresponding point on the unit circle that has some x-coordinate that doesn't matter, but the y-coordinate is roughly 0.86, and that is just sine of pi over 3, right? Sine of that particular angle gives us the height of this particular point on the unit circle above the x-axis. And again, sorry, I know I'm skipping all over the place here, but if we have pi over 2 as our input, we get 1 as our output. And how can we interpret that? Well, pi over 2 radians really looks like this as an angle in standard position, pi over 2 radians. And this is the corresponding point on the unit circle, right? This terminal arm intersects the unit circle here. We could call this our fourth point, which has some x value, doesn't really matter. And then what is the y value? Well, the y value is what we're interested in, and the y value is clearly 1, right? The y value must be 1 because the radius of a unit circle is 1, and this particular radius lies along the terminal arm going straight upward. So the height should also be 1 because it's going straight vertically upward. So here we have sine of pi over 2. And remember, for the unit circle, sine of the angle gives you the height of that particular point above the x-axis. And I won't do that for every single input and output value here, actually. It'll be too long. So let's look at 2 pi over 3. So 2 pi over 3 is the next tick mark over. It would just be pi over 2 radians plus pi over 6. So it's in the next unit over, plus pi over 6. What is the output? It is just a root 3 over 2 again, which makes sense. I'll quickly do that. So here is, I know I said I wouldn't. So here is the terminal arm for an angle of 2 pi over 3 radians. What would the height of this particular point be above the x-axis? Well, you might actually be able to see, and I'll do this in green, you might actually be able to see that the height of this particular point, let's call this P5, the height of this particular point above the unit circle, it should be the same as the height of the point above the unit circle. Sorry, it should be the same as the height of the point on the unit circle for point number 3. Right, they are ultimately at the same height. So here we have point 5, point number 5. It has a particular x value, it doesn't really matter, but the y value is roughly 0.86, or root 3 over 2 exactly. And this is really just sine of 2 pi over 3. And we can see that, well, this should have the same output as sine of pi over 3 because they have the same reference angle of just pi over 3 radians, and sine is positive in quadrant 2, so they should have the same output value. So that's why we get this same output value here for sine of pi over 3 and for sine of 2 pi over 3. All right, so let's keep moving on. We're going to have another repeated value here, actually. When we have sine of 5 pi over 6, we're going to get another output of 0.5. We've seen that output before. You can definitely notice that this is not a one-to-one function, right? We see the same output value again. And so let's plot this point at 5 pi over 6. We're going to have 0.5. And does that make sense? Absolutely, because at 5 pi over 6, we're going to have this corresponding terminal arm, and this particular point has a height that's going to be the same as, let's show in green, this particular point is going to have the same height above the x-axis as the point with the angle in standard position that had the same reference angle of pi over 6. So this point, this sixth point that has some x-coordinate that doesn't quite matter so much for sine, has an output value of 1/2, or 0.5. And that's the same output value as the second point that we were charting here, right? Because it's clear visually that these 2 points have the same height above the x-axis. That's very clear visually. And then when we make the connection that, well, this this height above the x-axis is really what sine of theta is giving us for corresponding points along the unit circle, then we can start to fill out this graph a little bit more intuitively. So let's look at this particular input and output pair for a rotation of pi radians. We're going to have 0 height above the x-axis. That works out, right? We have a rotation of pi radians. We will be right here with some x value. It'll just be -1, but that doesn't quite matter. And the y value will just be 0, right? Again, we're not really concerned about the x values for the sine graph. We're not concerned about the x values for the points along the unit circle. Cosine, that will matter for cosine, but it won't matter for sine. All we're interested in is the heights for sine. All right, so we have this point at pi and 0. And then we can clearly see that if we plug in a number like, if we plug in an angle like 7 pi over 6, if we plug in an angle like 7 pi over 6, let's go all the way over here, then we're actually going to have, another height. Let's call this point 8 with some x value. And what's the y value going to be? Well, it's sure as whatever, going to be negative, right? So here it looks like for point number 8 and point number 6, they are equal distances away from the x-axis, and so the y value for point number 8 is going to be equal but opposite to the y value for point number 6. It's going to be -0.5, and hey, that works out here. That's actually what they've given us in this chart. So when we have an input of 7 pi over 6, we have an output of -0.5. Right, so we have this ordered pair that we can plot on this two-dimensional coordinate grid like we've been doing. So -0.5. And yes, so that's sort of enough of the unit circle for now. Maybe maybe I'll completely forget that I said that and go back to charting, to showing you the corresponding points along the unit circle. But let's actually just try to fill out this graph. So when we have 4 pi over 3 radians, we're going to have -√3/2, or roughly -0.86 as an output. When we have 3 pi over 2 radians, that's going to be, oh, look at me. That's going to be, when we have 3 pi over 2 radians, we're actually going to be at a quadrantal angle. It corresponds to 270 degrees. And so what is the height of this point? What is the height of this point? That would ultimately be 0.10, because this is 0.9. What is the height of this point? Well, it has some x value, and the height of, the y value, it would be 1, right? Because we have an r value of 1, so it's a distance of 1 from the origin, but it's in the negative y direction. So -1 makes sense here. So when we have a input of 3 pi over 2, we should have a minimum value of -1. Here we go. That's the point on the graph. And then when we have an input of 5 pi over 3, we should have an output of -√3/2. Right here, we can see again, this function is clearly not 1-to-1 because we have the same outputs appearing more than once. In fact, the same outputs are going to appear an infinite number of times because this graph will repeat. So let's look at this ordered pair as well. For 11 pi over 6, we have -0.5, so that'll be right here. And for a full rotation of 2 pi radians, we're going to be back at 0, right? We're not going to be above or below the x-axis at all. We're going to be on the x-axis. So what's the height of that point on the unit circle? It's going to be 0. And again, like I said, oh, well, here, let's actually just sketch this. Let's see what this beautiful creation will look like. So we're just connecting all these points because it's a continuous function, meaning it's defined for all of these values, all these interpolated values in between these specific values that we've calculated. So here's the graph. It looks like a wave, and it's nice that it looks like a wave because it actually can describe wave behavior. But notice again, I mentioned that this is not a 1-to-1 function because we have outputs, identical outputs appearing for more than one input. And outputs are going to appear an infinite number of times, actually. They're going to repeat an infinite number of times. So we could actually continue the pattern of this graph. Here we can notice, actually, that what happens with our outputs. Well, Well, we go from 0 to 0.5. So we've got 0.5 here. We go from 0.5 to 0.86. So we should have 0.86 here. We go from 0.86 to 1. So we should have 1 here. We go from 1 to 0.86. So we should have 0.86 here, and so on. We have 0.5 here. We have 0 again. We have negative 0.5. We have negative 0.86, or negative root 3 over 2. We have negative 1, we have negative 0.86, we have negative 0.5, and we have 0 again. And we could just keep going, right? We could just keep going literally forever. So this is what the sine graph looks like. And this is a particular pattern that, funnily enough, we call a sinusoidal pattern. Sinusoidal pattern. And it's also called a sinusoidal function. So this is our first sinusoidal function, and just like, and again, this sort of continues forever to the right, and it continues forever to the left. It has an infinite domain, but you can notice that while it has an infinite domain, its range is quite restricted. Its range is only values. It is only valid for output values in between 1 and negative 1, right? We can't get any other outputs outside of that. So the height doesn't increase beyond this. The minimum value doesn't decrease beyond this, unless we transform the function itself, right? Unless we change the function by transforming it in some way, like stretching it vertically, which we can do. So here you go. That's the first sinusoidal function that we've drawn, and ultimately, what this is doing is it's showing us the pattern for the heights of different points above the unit circle as we increase our angle. And notice that we absolutely can increase our angle forever if we want. So we can find some output value for sine of, I don't know, 1,000,000 pi over 3 or something like that. What a mess that looks like, hey? So hopefully some of that landed. Hopefully some of it made sense. But it takes a while for this to really make a whole lot of sense as well, because it takes a while to really understand the unit circle in the first place, how it's defined, the relationship between the heights of different points along the unit circle and the sine of that corresponding angle in standard position. And then once you are comfortable enough with that, then you can plot those corresponding values of a particular angle in standard position and the corresponding height of that point on the unit circle above the x-axis, which is modeled by sine of theta.